For those of you new to this project, this is a FANUC R2000 industrial robot. We picked it up as industrial surplus a few years ago, but it unfortunately didn't come with the correct controller, so we were never able to run it at full power. To fix that, I made my own controller that uses Linux CNC and O drives to run the motors. It has been running like this for the past several months and is used by our Discord server members to stack blocks and crush cans. However, this controller is starting to give me issues and I need to restart it almost every day to keep it running. This is actually pretty good timing because the new controller I've been working on to replace this mess is finally just about far enough along that I can start testing it on the real robot. I now have the main controller up and running with one of my servo drives, so I can now run motors like the ones on the robot properly. We are working with PCBWay to make the new servo drives since I need to fix the issues I found on this version. I usually just assemble boards myself the first time, but after placing the hundreds of parts on this one, I decided I never want to do that again. This time I'll be using PCBWay's assembly service to get all the new servo drives assembled so I won't need to spend days hand placing a bunch of parts again. I'm going to get at least enough to run this entire robot, along with a couple more for testing, so pretty soon I should have the entire robot up and moving again. PCBWay also offers CNC machining and sheet metal fabrication, which is going to be particularly useful in my case. I need to get enclosures made for the servo drives, not only to keep everything safe once they're running at full voltage, but also to help reduce the EMI that big motor drives tend to cause. Visit them using the link in the description to get $5 off your first order and also help support the channel. I also realized I sort of skipped over talking about the whole open source thing on the last video I did on this. Everything is open. The files for all the PCBs and the software for the servo drive and everything in the Zinc are all available on GitHub. The repos are still a bit of a mess, and I'm working on getting them cleaned up. Everything's still in a sort of thrown together stage before it's fully locked down into a final layout. The goal of this new controller isn't just to run this robot though. If it was, I'd probably be done by now. The goal is to make something that can be used to run all sorts of different robots and machines without spending weeks learning how to configure everything each time. I have a long list of different projects that require various different controllers similar to this, so the obvious solution is to just make this one handle all of them. Things like CNCs, industrial robots, and even 3D printers are really not all that different. If you can handle the different motors and kinematics, the rest is just about the same in most cases. However, in practice, it's really hard to make stuff universal. There's a very fine balance between making it actually work for a bunch of different machines and having it be easily configurable. On the extremes, there's having to write the raw code from the ground up. This is obviously the most versatile, as there's zero existing code that might lock you into doing something a certain way. The downside is, of course, you need to write and figure out absolutely everything from the ground up, which takes an absurd amount of time and effort. On the other extreme, it's fully configured and works right out of the box. But this is only possible if the exact machine and use case is known beforehand and you limit how much can be configured. What I'm trying to get is the perfect balance between these sides. And let me tell you, I've spent a very long time running through different machine scenarios and planning just how to structure this entire thing. As of now, most of this stuff is either just on paper or only partially implemented for testing. It's all still very open to change. I'll get into the lower level stuff that actually is pretty locked down and actually functional in a bit. After much planning, I've broken the main configuration down into 3 big parts. First up is the motion diagram. The controller needs to know exactly how the physical machine is configured to be able to run it properly. The first part of this, which is still sort of the ugliest to set up, is the joints themselves, meaning how long each section is and where the joints are relative to one another. This is a 6-axis robot, which means it has 6 motors and 6 actuated joints. There are robots that have more and less, but 6-axis tends to be the most common because it lets you control the full position of whatever's attached to the end of the robot and what angle it's tilted at. The controller needs to know the exact position of each one of these joints and how long the links are between them to accurately control where the end of the robot is. The best I've come up with for this is literally building a simplified 3D model of the robot with the links and joints. This is what a few other common programs use to define or at least view the configurations. The issue is that setups can just vary so much that it's really hard to have anything much simpler without locking you into a specific setup. Once we have the joint layout, next up is the main part of the motion diagram. As much as I'd love to just assume that each one of those joints has a single motor controlling it, That would just be way too easy. For most machines, they connect straight through. In this robot, J1, 2, and 3 go directly into the gear reducer and then move the joint. However, the way the final 3 joints in the wrist are set up on this robot is a bit more complicated. The wrist has 3 joints in it, each of which are driven by one of the motors up on the top. The issue is, they are not directly linked as I originally thought. Currently, the controller is set up to turn one motor whenever it wants to turn one of those joints, which is obviously what you would assume, but if I put some pieces of tape on the wrist and move it, you'll be able to see that it's not exactly that simple. Okay, I think that's close enough. You should be able to see that the tape is perfectly aligned. Okay, now that we have finally completed one full turn of J4, you'll notice that both J5 and J6 have moved, even though the motors up top have held their exact position. Alright, let's crack this thing open. I need one of these motors down for testing anyway, off the robot. So now's as good a time as ever to look inside and see how this thing's actually driven. Hey, there's no bolts in the middle. There aren't any bolts down there. These motors only have 3 bolts on each one. They're skimping out. Brightest thing in frame now. Oh yes. What a mess. Alright, so I've taken off the J6 motor, so now we can actually see the gears that are down in there. Each of these motors has one of these gears on the end of it that meshes with its own one of those bigger gears down in the middle. Each one of those gears is then attached to a concentric shaft that runs down the center of the arm. So if we look, I should be able to move this motor back here, which is J4, and this motor, which is J5. I believe J4 should be the gear on the bottom, which is the biggest, because it needs to be on the outside of those shafts running down, since it's the first gear reducer it'll hit. The center gear should be J5, and then J6 should be the top, but the J6 motor is here, so we aren't going to be able to move that one. So when we try moving J4, see if the bottom gear moves. Yep. An interesting part you can actually see is even though I'm only commanding J4 to move, which is the bottom gear, you can see the top 2 gears are still moving, and even the gear on the end of J6, because of all the control loop issues I've been talking about in some of the previous videos. If the control loops were tighter on these motors, we wouldn't have that motion or sort of hunting back and forth. So at this point, we have those 3 concentric shafts running down this part of the arm. The outermost one of those shafts goes into J4, which is this reducer section right here. The center 2 remaining shafts that drive J5 and 6 pass through the center of that reducer and then down, sort of spread out into this other stuff. But for now, let's just focus on this section. This is actually what causes our first issue with those offsets. For a reducer to not move, the input needs to be stationary. But crucially, and I overlooked this, the input needs to be stationary relative to that reducer itself. The 2 shafts that pass through this reducer, if they're being held steady, meaning the motors up top are not turning, those shafts are stationary relative to everything above this joint. But now that they've passed through the reducer and the reducer is turning this output down here, those shafts are no longer stationary relative to it. Now there's a little bit of movement based on how far J4 is turned, and that sort of just translates down through into the reducers below, and that's what's causing these offsets. What we need to do to compensate for that is take the output position of this reducer and add that rotation or subtract it from the two shafts that pass through it. That way, if this is moving, we need those two inner shafts to move synchronously with it if we don't want the reducers below to move. There's a similar issue with J5. This joint back here, even though we don't have any shafts actually passing through it, the way the motion is connected through into J6 is still dependent on the angle of J5. Because of that, we're going to need to add or subtract the output value of J5 and put it into J6. Most machines are not nearly this complicated. Most of them are just motor directly into the joint, none of this weird offset stuff. But obviously this one is, so I'm sure other machines, even if they're rare, still need the same thing, and I want to make sure that this controller can handle that. The math behind actually doing the offsets is super simple, and the controller would have no problem doing it. The issue is figuring out how to make it easy to describe what you want it to do so it can run it properly. The confusing part is just laying it out and showing it in a way that's intuitive. This is what I've settled on. The joints themselves are added based on however the robot was configured in the previous step, and then it's up to me to add the motors and encoders and link everything together the correct way. For most setups, it'll look like this first joint. The lines that connect between the nodes essentially represent mechanical links between the parts. The motor is directly connected to the encoder and to the input of the gear reducer. Then the output of that is connected to the joint. This is also where all of the motor, encoder, and joint parameters can be configured, such as maximum speed, motor current, and encoder resolution. Now let's look at how this can handle the offset issues I have with the robot wrist. J4 is the first of the three motors we looked at earlier. It has two separate gear reductions before the end joint. One up at the top, which is pretty small, and then the much larger one at the joint itself. Technically, I could probably multiply those two reductions together and put it in as one block, but because they're physically separate, I'm going to just leave it as two. The only thing I need to add on the next joint is a subtraction block from the output of the previous joint to the shaft that passes through it. This effectively tells the system that if that joint turns, it needs to turn the shaft passing through it the same amount to ensure the output joint stays still. This diagram also allows me to add additional switches for limits or homing, or additional load encoders for more accurate positioning to any segment along the chain. It also makes it so I can jog and read back the calculated position of each one of these linkages, which I know I'm going to find super useful when it comes to actually testing and debugging this thing, especially these weird joints at the wrist. Once the motion diagram is fully completed, the controller has basically everything it could need to figure out where it needs to move the motors to get the robot where it wants. The fine details of the kinematics and path planning are outside the scope of this video. The main part here is just getting the machine defined in an at least relatively simple way. I'm sure a few of you are furiously typing away at some obscure setup that this can't represent, which is great, we have a Discord for that. I have pretty much only been planning for serial link robots, meaning each joint is stacked on top of the last. Parallel robots like Delta printers or Stuart platforms end up having a totally different way of being solved, so they've been pushed aside for now. But if you have a setup that you'd like to see if this could solve, then definitely post it. The whole goal of this thing is to be universal after all. Next up is the electrical diagram. This is much less of anything new. It's basically just an electrical schematic with some additional handling that lets the controller sort of figure out how to actually use it. Several of the parts like motors, encoders, and limit switches are directly linked from the motion diagram to ensure everything matches up. This is also where parameters like motor settings and current limits can be programmed in. Everything attached to the controller should ideally be represented here, although because there's just so much variety, many parts will simply be here to show that the part exists, but may not actually be factored into how the controller runs. This mostly just gives a nicer way to specify which ports everything is connected to and where all the inputs and outputs go. The final main part is the true core of the entire system and is what the motion diagram ends up getting converted into. It's not implemented far enough to go into deep detail, but I plan for it to use a similar interface to the other diagrams with nodes you can drag around and connect together. A massive part that I've considered through all of this configuration is trying to avoid needing to recompile or restart the entire controller to make changes. Most of the previous configs I went over all happen at runtime, and hence allow me to adjust values and see how it immediately affects the system without needing to stop and reboot every time. Which finally brings us to the part of the controller that isn't runtime configurable, but is also the most powerful. This is the stuff that's actually running and functional. I'm using a Zynq SoC as the main processor. It has 2 cores running Linux, and then an FPGA that I can write my own logic for. The FPGA lets me make special modules dedicated to certain functions. For instance, one of the issues with using these robots is finding a motor drive that can use the encoders they come with. They use a proprietary protocol that most drives don't support. However, it's nothing a logic analyzer and some effort can't solve, so I made a module that decodes it and outputs the position information. I have another module for talking with the servo drive and other future devices meant to go along with this system. Basically anything you can think of to interface with, you could make a module for it. Even though I can put whatever modules I want together to handle pretty much any machine, the entire process to reconfigure the FPGA is not exactly fast. All of the modules are written using Amaranth HDL, which is a Python module that lets me write FPGA code from within normal Python. I was already pretty familiar with Python when I started this, but the fundamental differences between writing normal code and describing the actual logic is quite the jump. If you're at all familiar with pretty much any sort of software programming language, you know that code gets run one line at a time, stepping through your entire program. However, when defining hardware, everything happens everywhere all at the same time. This is precisely how FPGAs can give you such good performance in some cases, since unlike a CPU which only does one thing at a time, an FPGA can do basically as many things as you want all at once, providing you don't run out of logic gates. I have the code set up so I just input which modules I want and how they're configured. In my case, I can change things like the total number of encoders a single encoder module can handle and how many drives I want to have on the same serial port. When I run it, it generates and exports a file for the FPGA and also makes another file that my software on the Zynq uses to know how to access and use all of the modules in the FPGA. But we aren't quite done yet. I need to go into the main project for the Zynq and load in that file we just generated. This is what takes the longest and is where the actual logic gets turned into the physical configuration of the thousands of gates inside the FPGA. Once that's done, I then copy that file over to the Zynq so it can load it into the FPGA on startup. All of this is a bit of a pain, and even though a lot of it is going to be automated so that there's only a single config file you have to mess with to build a new config, I'd still like to not need to do it for every little change. What I'd like to do is just include all of the commonly used modules and then configure how they're actually used later on. So I made another module that can be configured to move data around wherever I want between all the modules in the FPGA. The software configures it and then it runs all by itself to move data between the modules and processors, or even directly between the modules, which allows certain functions to run completely alone without ever needing to wait for the software. This is great since the data throughput between those modules is upwards of 3 gigabit, which gives it plenty of room to run updates insanely fast. The current setup I have here is only running at 1 kHz since I have the software run some of the control loops, but if they were done in an FPGA module, the whole thing could run at around 1 MHz, if it weren't for the encoder and servo drive communication being so slow in comparison. Now, being able to use basically any interface you want as long as you can reverse engineer it is super convenient, but there's much more the FPGA can do. Even with everything in it to run all 6 motors, there are still a ton of available resources. The real benefit FPGAs are usually used for is data processing. In my case, this would likely be stuff like helping offload the kinematics or path planning calculations from our processors to both run faster and more efficiently. Currently, I haven't gotten too far into that yet. Right now, I just have a very simple test setup running. A single motor running in position control mode, mostly just to get the low-level communication and interfaces working. Now I know what you're thinking. He could have just bought a $100 motor drive to do that instead of spending 200 hours on that thing. And to that I'd say, for one, yes. For two, it will eventually be much more capable. The progress tends to be very chaotic. I spent a few weeks just getting the motor controller to communicate with the drive, but then the position and velocity control loops took only 30 minutes. Once the lower stuff is tested and working, the higher level stuff tends to move along much easier. And for three, it's much more than 200 hours. The amount of time I've spent getting this stupid little chip to do what I want makes aimbot and fire laser seem like nothing. 99% of it is just software and hardware debugging, so it doesn't exactly make for the most interesting video, but now it's actually doing something physical, so there's something to look at. The FPGA is getting data from the encoder, then sending the commutation data directly to the servo drive so it can run the motor, and then sending the encoder position to the software. The controller software then runs velocity and position control loops to figure out how much torque the motor should apply to reach the commanded position. The FPGA then takes that and also sends it to the drive. The drive itself is actually pretty dumb and only regulates the current through the motor, which is proportional to the torque. No velocity or position control actually happens on it. I designed this drive to handle running motors like this up to 400 volts and about 60 amps. Even though they're rated for much less on the nameplate, they're designed to handle 300% overload for short periods, and I wanted to make sure these drives wouldn't limit it too much. You may have noticed this isn't running anywhere near 400 volts. 400 volts is a lot, and it's more than enough to vaporize some components if something goes wrong, or even be lethal if touched. So for testing, I've been running under 50 volts, which prevents anything too exciting from happening. This board revision has several issues, so I'm going to get those fixed on the next batch instead of trying to push it and potentially blowing up the only board I have for testing. There is also now a deadline to have a robot fully functional. We went to an event last year to show off some of our projects. I actually originally planned on taking a setup similar to this to run a motor, but ended up not having quite enough time to get everything working reliably. We ended up taking aimbot and the non-functioning servo drive just to show, along with some thrown together badges to hand out that ironically ended up being the most popular thing we brought. There was a surprising number of people who were still really interested in the robot controller project, which was really good to see since it's actually been one of my favorite projects to work on. So the plan is to bring a working robot and controller this year. Quite the leap from where it's at now, so exactly what counts as fully functional might change around a bit. You can join the Patreon or Discord if you want to support or discuss more about this project. Thanks for watching.